Hello, good morning students. Now we'll continue with our previous lecture of hemoglobin 1, that is hemoglobin 2. Further, hemoglobin, as you all know, we have already studied that it is composed of 4 polypeptide chains, which in adult consist of 2 alpha globin chain and 2 beta globin chain. Each polypeptide has a heme prostatic group attached where each heme can bind one oxygen molecule. So there are 4 heme groups per hemoglobin molecule and they can bind 4 O2 molecule. So hemoglobin is synthesized in complex series of steps. The heme part is synthesized in series of steps in the mitochondria and the cytosol of immature RBC, while the globin part is synthesized by the ribosome in the cytosol. So heme part in mitochondria and cytosol, whereas globin part by the ribosomes in the cytosol. So production of hemoglobin continues in the cell throughout the early development from the proerythroblast to the reticulocyte in the bone marrow. At this point, the nucleus is lost in the mammalian RBC but not in birds and other species. Even after the loss of nucleus in the mammal, the residual ribosomal RNA allows further synthesis of hemoglobin until the reticulocyte loses its RNA soon after entering the vasculature. That is, this hemoglobin synthesis RNA in fact gives the reticulocyte its reticulated appearance as it is named. The glycine is the precursor of porphyrins. Very important. A heme group consists of an iron held in a heterocycle ring known as porphyrin. This porphyrin ring consists of 4 pyrrole molecules cyclically linked together by methane bridges with the iron bound in the center. The iron, which is the site of oxygen binding, coordinates with the 4 nitrogen in the center of ring, which all lies in one plane. The iron is bound strongly to globin proteins via imidazyl ring of the F8 histidine residues below the porphyrin ring. The sixth position can reversibly bind oxygen by coordinate covalent bond completing the octahedral group of 6 ligands. Oxygen binds in an end-to-end on band geometry where one oxygen molecule binds Fe and the other protrudes at an angle. When oxygen is not bound, a very weakly bonded water molecule fills the site, forming a distorted octahedron. Even though carbon dioxide is carried by hemoglobin, it does not compete with oxygen for the iron binding position, but it actually binds to a protein chain of the structure. The iron molecule may be either in Fe2 plus or 3 plus state, but hemoglobin, that is methemoglobin F3 cannot bind oxygen. In binding, oxygen temporarily and reversibly oxidize F2 to F3 while oxygen temporarily turns into superoxide. Thus, iron must exist in +2 oxidation state to bind oxygen. If superoxide ion associates to F3 plus is protonated, the hemoglobin iron will remain oxidized and incapable of binding oxygen. In such cases, enzyme methemoglobin reductase will be able to eventually reactivate methemoglobin by reducing the iron center. When red cells reaches the end of their life due to aging or defects, they are broken down in spleen. the hemoglobin molecule is broken up and the iron gets recycled. When the porphyrin ring is broken up, the fragments are normally secreted in the bile by the liver. This process also produces one molecule of carbon monoxide for every molecule of heme degraded. Another major final product of heme degradation is bilirubin. Increased level of these chemicals are detected in the blood if red cells are being destroyed more rapidly than the usual. Improperly degraded hemoglobin protein releases from the blood cells too rapidly can clog small blood vessels of the kidney, causing kidney damage. Iron is removed from heme and salvaged for later use. It is stored as hemosiderin or ferritin in the tissues and transported in plasma by beta globulin as transferins. Heme is degraded to bilirubin. Liver secretes bilirubin into the intestine as bile. Intestine metabolizes bilirubin into urobilinogen. Urobilinogen leaves the body in the fecal matter. It is a pigment stereoglobulin. Globin is metabolized into amino acid and released into the circulation. So for the degradation of RBCs in vertebrates, various steps they are there. That is, we'll start with bone marrow. In the bone marrow, erythropoiesis is there. Erythrocytes they are produced. So these erythrocytes, they'll travel for 120 days. They will for 120 days carry oxygen and carbon dioxide from lungs to tissues to the lungs. When the aged or the damaged erythrocytes they are there, they'll come to the liver, where the hemoglobin is broken into two parts, heme and globin. Globin part is a protein part which is converted into the amino acid, whereas the heme part is degraded to bilirubin. This bilirubin through the liver is thrown out into the intestine as a fecal matter. So in this way, the destruction of RBCs is there with the macrophages in the spleen and the liver. So sincere thanks to www.google.com for providing us beautiful pics for the explanation of the topic. Thank you.